In classical mechanics, we know that Newton's laws of motion dictate events. However, these laws are not universal. As we approach events occurring on the very small scale, we have a different set of rules we must use. These rules for the very small comprise quantum mechanics. We are going to focus on one of these rules, known as the Heisenberg uncertainty principle. To properly explain this rule, however, we must first explain the wave function. A wave function is a sort of equation that describes a quantum system. This wave function can be used to find all kinds of information about any given system. One way a wave function can give us information is through something called operators. Operators allow us to pull specific information out of a wave function. Two important pieces of information are position and momentum. By having these operators act on a wave function, we can solve for their average value. What this means is that by implementing operators, we can solve for the mean of four important values: position, position squared, momentum, and momentum squared. Using this, we can solve for something called standard deviation. Standard deviation tells us how varied from the mean measurements are, or more simply, how spread out the data is. Now let's say that you prepare a system such that when you take a series of position measurements, the results will always be very close together. This means that your measurements will have a very low spread, and as such, a very low standard deviation. Now let us say that for this same system, you also choose to measure momentum, hoping to get an equally precise result. Sadly, when you take these measurements, you will find that the standard deviation is quite large, and your measurements very spread out. This is the basis of the Heisenberg uncertainty principle, which states that the standard deviation of position times the standard deviation of the momentum will always be larger than the reduced Planck's constant over 2. What this means is that for any state, and I do mean any state, it is impossible to precisely know a particle's position and speed. An important thing to note is that this is not some limitation of current technology. The Heisenberg uncertainty principle is absolute, meaning that for any particle, anywhere, it is impossible to precisely know both its position and momentum. To do so would be physically and mathematically impossible. Here we have a real-world example of the Heisenberg uncertainty principle at work. This laser is pointed at a black sheet. As a shutter covers the laser's light, we can begin to see that light spread out right before it disappears. What is happening is the position of the photons is becoming restricted, and as such, their velocity is becoming uncertain, causing it to spread out, as we can see here. So a question you might have is, why does this not apply to large-scale systems? For that matter, why doesn't all of quantum mechanics apply to large-scale systems? The answer to that is simple. We don't know. At present, we have no all-encompassing set of rules that applies in all systems. We just have classical systems and quantum systems. Sometimes you have to use quantum mechanics, and sometimes you have to use classical mechanics.